Hi, going to talk about the material from Lecture 2 this time. Right, Lecture 2, it's got a bunch of things in it, not too many. Discrete and continuous data sets, a little bit about sampling, and then stuff about data lists and frequency tables. As always, watching this video or these videos is not a substitute for reading the book and notes. There may be material in those that you will need that I do not go over here. Okay, let's start out with discrete and continuous. Right? We're talking about data here. It has to be numerical data we're talking about. Right? That is quantitative data, the result of measuring or counting. And we're going to divide up this kind of data into two different types. First, there is continuous data, as we say. This is, it can take on any value in some interval. We'll talk more about this in a minute when we do an example. And then there's the discrete type of data. And this can only be values from a set that can be counted out, listed. So here's my favorite example. Consider this data set. Now this problem only really arises. The problem of being able to distinguish between continuous and discrete only really arises for data sets that are described. Right? When you're actually given numbers or something, then it's usually not a problem. But if you're just given a description, you might have to decide whether what's being described is a continuous or a discrete data set. So here's an example. The number of whole unbroken eggs in a carton. Right? And let's suppose we're just talking about cartons that can hold 12 eggs here. Okay. Well, what are the possible numbers that could be described by this? Well, let's put them on a number line. The number line is the best way to think about this. You could go to your favorite grocery store, open a carton of eggs, and start counting how many were whole and unbroken. You could find them all broken, in which case 0 is a possible value. Right? 1 is a possible value. 2 is a possible value, and so on all the way up to 12. Right? Those are the possible values, 0, 1, 2, all the way up to 12. Right? But it is not possible to find, let's say, 2.7 whole unbroken eggs in a carton. That's just not possible. So when this kind of thing happens, when you plot the data, the possible data that could be in this set, the possible values, right, and you get individual dots on a number line separated by spaces, right, then this is going to be a discrete data set. There are only a certain number of there are only certain individual values that can be described by this. Here's another one. How about weight of a carton of 12 eggs? Well, what are the possible values here? Let's see, is 0 a possible value? I actually don't think so, right? Because you'd have to have at least a carton. I don't know what the smallest number is. It could be the lightest carton, but let's say it's this value right here. Right? We'll call it C. Right? In any case, you could have a carton of eggs weigh 1 pound, or 2 pounds, or 3 pounds, or any other number of pounds up to some maximum, which we don't know. But the thing is, you can also have a carton of eggs that weighs, and so 1 and 2 and 3 are possible values, but so is 2.764. Right? And so is 3.14159. Right? In fact, any number, starting with this value c, which is the lightest you can have, any number from that point on up can be the weight of a carton of eggs. This in the picture on a number line, you'd have to shade the entire interval from C on up to whatever the maximum might be. Right? It would not be individual points separated by spaces. This is continuous data. That's the way to tell. Okay, we'll come back to that in, I don't know, a few weeks. All right, I have to say a few words about sampling. Let's do this. So I need to scribble as I talk. Sampling. I said a few words about it before. Sampling, when you take a sample, a subset out of a population, you want to get a sample that is representative of the population. And again, what that means is that if you make some calculation from the sample data, and you make the same calculation from the population data, the calculation from the sample data should be pretty close to the one from the population data. Right? That's what representative really means. The best possible sample is called a census. Right? A census means the sample is in fact the whole population. This has to be mentioned. In real work, it almost never happens, as you know. Right? The United States Constitution calls for a census no less frequently than once every 10 years, and we have a multi-billion-dollar Bureau of the Census that tries very hard to count every single American. It can't, of course, and it knows it, but it has to keep trying because the Constitution does not allow for statistical corrections, and no law has allowed for it either in the United States. In some countries they are used, and it probably eventually will be here. They're computed, but they're not allowed to be used for what the census is really intended for, and that is setting the number of seats that each state gets in the House of Representatives. Anyway, a census is the best thing you can have, but you're not going to get it, right, in real work. So the second best kind of sample to have is called a simple random sample. And we're not going to give, that's supposed to say random, we're not going to give the technical definition of simple random sample here. Not that it's that difficult, but it's not, there's really no point to it. But you can think of, if you see in a problem or if you hear someone say, chosen at random, we chose 1,000 Americans at random or whatever, you can rely on it being a simple random sample, at least in textbook problems and such. There is a whole discipline of sampling to deal with, including tiny minorities. And if you wanted a sample of the American people that included Sikhs, for example, to look for opinions, well, I don't know, you'd probably have to choose 100,000 people at random before you even got one Sikh, because there are so few of them in the U.S. Right? So you'd need some way to deal with that. And there are all kinds of techniques for dealing with that. In here, we're just going to assume that our samples are simple random samples unless something says otherwise. Except now and then in a problem that asks you to determine whether something's probably a simple random sample, and then you have to do that. But if something just says, 50 gas stations were chosen in Elizabeth, New Jersey, well, you can think they were chosen such that it's a simple random sample. Okay, a couple of words around this. Right? When you compute a statistic from a population, a statistic from a sample, and a corresponding parameter from the population, it's very likely that they won't be equal. The statistic is, after all, just an estimate for the population. It's not going to be equal because you don't have all the values. And the difference is called sampling error. Right? And all that sampling error is the difference between a statistic and the parameter it's supposed to estimate. And this kind of error doesn't arise because of human error, because of errors in theory. It's simply that the statistic is found from some of the values and the parameter is found from all of the values, so they're really computed from different sets. Right? It's still called an error because the statistic is not equal to the parameter, but it doesn't arise from any kind of mistake. Okay, let me talk about a couple of ways in which we present data. Right? The first way is called just a data list. Right? And a data list is just as simple as it sounds, right? It's just a list of data values, 12, 14, 13.25, whatever, right? Or, green, red, blue, anything that just lists data values. That's just called a data list. There's nothing more to be said about that. The other way that we're interested in is called a frequency table, and there are really two types of those. Right? A frequency table, or better would be frequency distribution. Right? That's the kind of the technical term. It is just a table. Right? All it is a list of data values and the frequency of each one. The frequency of each value. That is the number of times the value occurs. So for example, if your data set is 1, 2, 3, 3, 3, 4, 5, then your frequency distribution would probably look like this. You'd have a column labeled maybe value and a column labeled frequency. In the value column, you'd list each separate value that occurred. 1, 2, 3, 4, 5. And in the frequency column, next to each value, you'd list its frequency, the number of times it occurred. So there's 1, 1, there's 1, 2, there are 3 3s, there's 1, 4, and 1, 5. And that would be a frequency distribution. Now this kind of frequency distribution is for what's called ungrouped data. That is, each data value is listed separately. Right? So I'm just going to write this ungrouped. The data here is ungrouped. It has not been, again, each data value is listed separately. It has not been grouped together in any way. All right. The same sort of thing for grouped data. For grouped data, what is meant is that you have your data already grouped together. For example, if you went out and sampled 5,000 Americans at random and asked them their salary or annual income, right, you would end up with a table that looked like this probably. Let's say salary range and frequency. Frequency of how many people in each range. So your early range might be, say, 0 to 20,000. And the next one would be something like 20,000 to 40,000. And 40 to 60, and so on. Well, let's just put this in here. 60,000 or more. Okay. And you might have, 297, let's say, people in this category. I don't really know. And 2,000 321 people in this category, and so on. Right? It would just be how many people had salaries in this range and how many people had salaries in this range, and so on. This is called grouped data because you don't have the individual values listed here. You have groups. And very often this column is labeled interval. Sometimes you don't have a good name like salary range, and then you just call it the interval column or class column. These are called intervals. Of course, they are intervals, and they're also often called classes. Right? You can see here that each of these classes, each of these intervals, is $20,000 in this case. Right? These are dollars wide. So this is from 0 to 20,000, 20,000 to 40,000, 40,000 to 60,000. If you plotted those on a number line, right? If you had 0 here, 20,000 here, 40,000 here, 60,000 here, these intervals would all have the same width. And that's going to always happen for us. Right? Their intervals are all going to have the same width, except possibly once in a while you may have this kind of interval that is semi-infinite, goes from some point on up forever. Right? When you need to represent 60,000 or more, or something like that. Okay. One more word about this. The class width in a frequency distribution table like this is this width right here. If you put these on a number line and measured this distance would be 20,000 from here to here, here to here. Right? It is the width of a class. Right? And when if you were ever asked for a class width in a problem, which once in a while you might be, there would not be a class like this, or else it would ask you for the width of a particular class. I haven't pointed out one thing, one possible problem that can occur. Suppose you have made this table and you are going through your list of salaries, right? And you're counting how many are in here, how many are here, and so on. Suppose you see the number 20,000. Where does it go? Does it go into this class or does it go into this class? And the answer is it always goes into the higher class. Right? You would put 20,000 in here, you would put 40,000 in here, not here, so on. Right? If you have a class that looks like 0 to 20,000, right? That means in interval notation, the interval that includes 0 but does not include 20,000. On a number line, it would look like this: 0, 20,000. Right? There would be a filled in dot here and an open dot here in the usual number line coloring in notation. 20,000 goes into the next interval, and that's always going to be the case for us. All right. I think that is all I need to say about this lecture.